Good morning, all of you. So today we will start with a small part of engineering properties of food material, that is steady state heat transfer, and our discussion will be confined to conduction. Now, why are we talking about this engineering properties? So in engineering properties, or precisely I can say thermal properties. Why do we need to study about that? So here it is written that the thermal properties like specific heat, thermal conductivity, thermal diffusivity, enthalpy, surface heat transfer coefficient, emissivity, etc. are important for the development of any thermal processing system. Okay, so any thermal processing system means what? Means that those can be used for heating, cooling, freezing, drying, etc. So for heating, cooling means how much heat can be transferred from one region to another, how much heat is getting absorbed within the body of the food material, or means since we are talking about the properties of engineering properties of food materials, so that's why I am giving examples of those. Means how much energy is getting absorbed, how much is getting reflected or transmitted. So based on that, we can design any system. Now going to the thermal properties, so I have not given too much details about it. Still, to study about the heat transfer or the mode of heat transfer, a little bit idea, or actually I should say the proper idea of thermal properties is needed. So in brief, I will say, what do you mean by specific heat? Specific heat means the amount of heat which should be added to or removed from any 1 kg substance to change its temperature by 1 degree Celsius. So that is a huge thing. Means if I want to change my change the temperature of my food material from say 20 degrees Celsius to 21 degrees Celsius, then how much heat I need to give it? Or if I want to cool it down from 21 degrees Celsius to 20 degrees Celsius, how much heat I need to extract from it? So that is your specific heat. Now when I am talking about that how much heat needs to be extracted or how much heat needs to be put into the system, then comes enthalpy. Means enthalpy comes into the picture. Now what do you mean by enthalpy? Enthalpy means the heat content within the body or energy content within the body. Now in case of specific heat and enthalpy, if my food material have lot of moisture within it, precisely I can say if it is more than 8% moisture content, then I have to calculate specific heat and enthalpy for the bone dry material as well as the moisture content of the material. So that is why you can see that how important these properties are for defining any food material or to process any food material. Then comes thermal conductivity. From the name itself, you can understand that what is thermal conductivity. Thermal conductivity means ability of a body to conduct heat from one region to another, or from a region of higher temperature zone to the region of lower temperature zone. Natural progression. Then comes thermal diffusivity. Thermal diffusivity is nothing but a ratio of a material, ratio of the ability of a material to conduct heat to its ability to store the heat. By formula, I can write here, thermal diffusivity is given by alpha, which is K by rho Cp, where K is my thermal conductivity, rho is the density of the material, and Cp is the specific heat of the material. So this thermal diffusivity, all these properties are highly important to understand that how heat is propagating through a body or how much heat is getting absorbed by the body. So now there are some other thermal properties also, like melting or freezing points. So melting point and freezing point, these are means why are we talking about this? Because for any pure substance, you will have a single melting point or single freezing point. But when we are talking about food materials are combination of various elements: carbohydrates, proteins, fats, moistures, vitamins, minerals, etc. Now all these different elements have different freezing points, different melting points, different enthalpies, different specific heat. So the melting point and freezing, we cannot get a proper or the exact melting point or freezing point. We will get a range. Okay, you have heard about freezing point depression or boiling point elevation. So this happens because of this variation in composition. So that is why we need to talk about this melting or freezing point whenever we are talking about heat transfer. Then latent heat we know. So latent, there are two types of heat transfer. One is sensible heat transfer and there is latent heat transfer, or sensible heat change or latent heat change. Latent heats are mainly when we are concerned about the change in the phase, that is from solid to liquid, liquid to gas, etc. Then heat of adsorption, whenever anything means whenever during any reaction or anything, if their adsorption is going on, then some heat is released or maybe some heat is absorbed. So that is why heat of adsorption is needed, and heat of respiration also. If we are constructing any refrigerator or any cooling system, then we need to take into account the heat of respiration of all living, or you can say if refrigeration and in cooling system, we generally keep the food items. So those food items, those can be climacteric food items or non-climacteric food items. So for climacteric food items, they can respire. So we need to take into account the heat of respiration, because that respiration heat is also needs to be extracted out from the cooling system. Then coefficient of thermal expansion is also there, because we have studied in school also that whenever you heat a material, there its volume and its length can also change. Now if its volume and length change, now just imagine if I am designing any heating equipment or any dryer or any freezer. Now because of the change of temperature, if the dimension of my system changes, so that will lead to hazard. Means if it is not controlled, then it can lead to hazard. It can lead to leaks, then it can also lead to cracks. So that's why thermal expansion is also important. Now why do we do heat treatments? So heat treatments to CDLs like wheat and maize, they are done or they are conducted. For pulses also they are conducted for stimulating germination. Then it can also be done for thermal killing of insect pest in storage. Okay, so most of our food materials, they get damaged or they get spoiled because of insect infestation in storage structure. Means almost 20 to 30% of our produce is being utilized, others get wasted. So that is why this insect killing, thermal killing of insect, so that is a major unit operation in any storage system. And then heat treatment is also given to the fruits for fruit fly quarantine disinfection. So that is also a kind of isolation or disinfecting our food materials. So for that also thermal killing or heat treatment is necessary. Then in all the calculations of heat treatment, the heat balance for heating is worked out with the knowledge of specific heat and thermal conductivity. Now to simulate or to model any system, means if I want to design any material, design any machine, so first what I know means two things I need to do. One is mass balance, another is heat balance. So for this heat balance, we need to know about all the properties, as I already said, that's the enthalpy, specific heat, etc. Okay, like how much heat is getting into the system, if any the heat is generated within the system, if the heat is getting accumulated within the system, and how much heat is getting out of the system. So we need a proper heat balance where a left hand side equation will be equal to the right hand side equation. So that if I can means those balances are needed for any design purpose. To design a dryer, the calculation of heat requirement is most important step. So for designing a dryer, I need to understand what is the mechanism of the heat. I need mechanism of heat transfer I want to give or I want to achieve. Then which kind of food material I can keep within the dryer. What are the limitations or what are the heat tolerance of those food material. what kind of material material I need to have to construct a proper dryer. So all these things are needed. Then for calculation of sensible and latent heat requirement, the thermal properties like specific heat and thermal conductivity should be known. So sensible and latent heat requirement. Sensible heat means whenever there is a change in temperature. Latent heat means, as I already said, it involves only phase change. The enzymatic activities and attack of microorganisms on fruits and vegetables can be minimized for extending shelf life by lowering the storage temperature. So these thermal properties, they are utilized not only for heating, but they are also utilized for cooling, as I said. So most of the enzymatic activities and also the microbial activity, they need an optimum temperature. So if I can reduce the temperature, or if I can bring down the temperature below that optimum temperature, then I can extend the shelf life of my food material. So for that case also, this the knowledge about thermal properties and also heat transfer is necessary. Now coming to steady state heat transfer. So heat transfer is one of the most important unit operations in the agricultural processing activities. Example, thermal treatment of food grains, cooling of perishables. Cooling of perishables means highly perishable food which have lower shelf life. Then pasteurization and sterilization of milk and fruit juices. What do you mean by pasteurization? Pasteurization means heat treatment to kill the pathogenic microorganisms, and sterilization is the thermal killing of both pathogenic and spoilage microorganisms to increase the shelf life of my products, and then freezing, etc. So I already discussed about this. Now it is also an essential operation to provide energy for evaporation of moisture during drying, solar heating or cooling, distillation process, etc. So provide energy when does evaporation occurs. Evaporation is also the phase change thing. So whenever water molecule, it changes from its phase from liquid to gaseous state, so its energy level changes. So that energy level is given is due to the enthalpy change. So that is why again it is directly related. The heat transfer occurs because of temperature difference driving force. So for anything to occur, we need a driving force, and we need a potential difference. Now what is a potential difference here? Here potential difference is my temperature difference. If there is a temperature gradient, means if I have a higher temperature zone and a lower temperature zone, then only heat transfer can occur. If both the other regions are at the same temperature zone, no heat transfer is possible. Now, so naturally heat flows from the high to the low temperature region. Now specifically for heat transfer, we get a balanced equation. Again, I am telling balanced equation is necessary. So what are the components of that balanced equation? I have already discussed, I have already said, rate of heat in, that is rate of heat introduced into the system, plus rate of heat generation. So when after introduction of heat within the system, reactions will occur. So that reaction can be exothermic. So in that case, heat can be generated within the system. So that is your left hand side. So that should be equal to rate of heat out. That is rate of heat coming out of the system plus rate of heat accumulation, if any. So heat can also get accumulated within the system if it is an endothermic reaction. So now consider one control volume here. Okay. So now we will discuss only about conduction. We will discuss about the heat balance using this conductive heat balance. So let us consider one control volume here. Here this location is x, and this location is x plus delta x. What is delta x? Delta x is nothing but the thickness of the control volume. Okay, means from this is a phase which is exposed to heat, and this is the phase from where heat is going out. So from this area to this area, so this rate in the thickness is delta x. So assuming the rate of heat transfer, rate of transfer of heat occurs only by conduction, we can write Qx by A. Qx by A is a heat flux. Qx by A equals to minus small k into ddx of T, or rate of change of temperature with respect to the thickness. So now, before going to the steady state heat transfer, so let me consider the unsteady state heat transfer, or I should say that I should consider the whole elements, means whatever is possible. Let me first think about that, or let me first discuss about that. So making an unsteady state heat balance for the x direction only. So why means here I am writing x here because I am now I will discuss only about unidirectional heat flow. So let that heat flow is occurring at x direction. So for x direction only on the element of a control volume. So this is a control volume. You can see a tube. So by using equations 5.8, what was equation 5.8? So this was equation 5.8, rate of heat in plus rate of heat generation, etc. And equation 5.9. So I'll tell you which equation is this in the subsequent slides. So and this control volume has an area, cross-sectional area of A meter square. So rate of heat within the system, heat means introduced within the system, is given as Qxx. So since the heat is propagating in the x direction only, so that is why this suffix x is given. So this Qx is the heat content or heat present in the region x here, this region. Since it is present at this region, so that is why it is written as Qx bar x plus Q dot into delta x into A. Q dot is the rate of heat generated per unit volume. So since means for unsteady state, rate of heat introduction plus rate of heat generated within the system. So I have given this factor Q dot, that is rate of heat generated per unit volume, into delta x into A. What is delta x into A? Delta x into A is the total volume, area into the thickness. That is equals to Qx slash x plus delta x. So Qx slash x plus delta x is the heat content or heat present with in this region, that is at the region of x plus delta x. So Qx x bar x plus delta x, so that is your heat coming out of the system plus heat accumulated within the system. This heat accumulated within the system is nothing but the enthalpy within the system. So this enthalpy is given by the formula mCp delta T. It is given by mCp delta T. Okay. So here Cp means a specific heat. Now the formula, what is given here? It is given here rho Cp del small t of capital T, that is rate of change of temperature with respect to time into volume of the control element, or means delta x into A. So this is volume of this area, this volume of this control element. So this volume into rho means the density. So then the formula of density or the unit of density is kg per meter cube, and this is meter cube. So meter cube gets cut. So I'll be left with mass only. So I'll get it in the form of mCp delta T. And here this temperature is changing with respect to time. So that gives you the enthalpy of the system. So this is already done. Now assuming no heat generation and also assuming steady state heat transfer where the rate of accumulation is 0, I'll be left with only this much portion. What means? What did I just say? So assuming no heat generation. So if I assume there is no heat generation, so this portion will get cut. And if I consider a steady state heat transfer means there will be no change in temperature with respect to time. So this will be equal to 0. So if this becomes 0, so that means this total thing will become 0. So I will be left with Qx means rate of heat input by conduction equals to rate of heat output by conduction. So no heat generation, no heat accumulation. So so that is why in steady state heat transfer I can say Qx is constant with time. That is means my rate of heat transfer will be constant with time. It won't change with time, and the temperature at various points in the system won't change with time. So that is a criteria for the steady state heat transfer. Now going into the further details or going into some problem solving for conduction. So let me just give you a brief of the three modes of or three mechanisms of heat transfer. So first we were already discussing about, that is conduction. So in short, conduction can happen through the solids, liquids and gas, all the mediums. It can utilize all the mediums, and here the material itself does not change its position from one place to another, but it just transfers the energy from one molecule to another. So heat is conducted by the transfer of energy between adjacent molecules. So see, here is one picture. So this is a, you can consider this is an iron bar, and here there is a heat source. Okay, now this iron bar is getting heated up at this area. And here if I put a thermometer, I will see that gradually the temperature is increasing. And now if you keep two more thermometers just few meters away from this heating source, you will see that the temperature is lower at those regions. So of course this will be at the highest temperature zone, and then here the temperature will be the lowest. But gradually if I keep on heating it, means if the heat is not, it does not change with time, or temperature does not change with time, gradually we will see that the heat has been distributed evenly here. So here the thermometer marking will increase, and again gradually here also thermometer marking will increase. So mainly the temperature will increase. Now energy can also be transferred by free electrons if we are working with metals or metallic solids. Now what are the examples of conductive heat transfer? Those are heat transfer through walls of exchangers, or means walls of heat exchangers or refrigerator, drum drying, freezing of the ground during winter, and so on. So this is mainly the indirect mode of heating. Okay, so if you have a cold substance and heating source, and in between if you keep a wall, then the energy will be transferred through the wall. So your both the heating medium and I can say the heated medium or heated product and the heating source, they are not in direct contact, still they are getting heated, or still the energy is getting transferred. So this is the indirect mode of heating. Then drum drying. If means many of you are familiar with the drum dryers. So what do you have in the drum dryers? So in drum dryer, I am the basic mechanism is that, or basic structure is that you will have one hollow drum or hollow cylinder kind of structure. Within that you will have a heating source, and that heating source will heat up the whole drum. Means the walls of the drums will get heated up, and over the surface of the drum you will put a pasty food substance or any liquid, semi-liquid kind of food substance. You will spread it over the surface of the drum, and the drum will be rotated. Now while rotating it, while rotation of the drum, the semi-liquid substance will gradually get dried up. It will turn into a flaky substance, and after 3/4 rotation it gets scraped by knife. So that is another means conductive mode of heating. Now coming to convection. So main difference between conduction and convection is that during convection there is an actual movement of the heated means warm molecules and cold molecules. So heat transferred by bulk transport and mixing of macroscopic elements of warmer with cooler portions of a gas or liquid, means there will be a mingling up of warmer region with the cooler regions. It also refers to the energy exchange between a solid surface and a fluid. So that fluid can both be, it can be both liquid and gas. So means if this wall if it gets heated up and I have air in this room, so the air will also get heated up due to the contact with this heated wall. A distinction must be made between forced convection heat transfer, means there are two types of convection. One is forced convection, another is natural convection. So forced convection is like we will use an external aid, maybe a blower, maybe an agitator. Okay, so that blower can evacuate, or it can replace the hotter air with the colder air to accelerate the heat transfer, or the agitator can be means done to start the water so that the warmer water molecules get replaced by the colder water molecules. So that can means that those are all done generally to accelerate heat transfer. Otherwise, natural convection may also happen where only density difference will cause the change in space or cause the transfer. Means if you boil certain water in a kettle, this is a kettle where water is getting boiled. Now because of this heating source, the bottom surface of this kettle will get heated up, and from this heated solid surface, the bottom layer of the water will get heated up. Now when water molecules get heated up, its density becomes lower, means it becomes lighter. So when it becomes lighter, it will try to move up. And whereas at the top, the water molecules are comparatively cooler, so they are heavier. so they will come down. So in this way circulation will occur, and gradually my whole water body will get heated up. So this is a very nice example of natural convection. And now if I just put a ladle here and just stir it, so then it will become a forced convective heat transfer. Now examples are loss of heat from a car radiator where the air is circulated by a fan, so that is a forced convection. Cooking of vessels in a vessel, cooking of foods in a vessel being stirred, again forced convection. Cooling of a hot cup of coffee by blowing over the surface. So here my mouth is the external source where I am blowing the air over the coffee, so I am replacing it with the cooler air. So again heat transfer is getting accelerated. And then comes radiation. Radiation is completely different from conduction and convection. Here we do not need any kind of medium. It travels just the way light travels from sun to earth. So it travels through electromagnetic waves. Now in electromagnetic waves we have two components, which one is magnetic component, another is your electric component, which are perpendicular to each other, and the direction towards which it flows, that is again perpendicular to both of them. So that does not need any medium. If you put any medium there, so that radiative heat transfer, it will get absorbed by the material, it will get transmitted through the material, it may also get reflected, as happens with the sun rays. So reflected and refracted, everything will, means all those things will happen. So generally radiation is more important when it is going through the space. So examples are transport of heat to the earth from sun, cooking of food when passed below red hot wires, means, or if it is a microwave, in microwave heating it is nothing but a radiative heat transfer. So now all these mechanism of heat transfer, those are not in any isolated islands, those always happen in combination. Okay, so and their concomitant results give us our practical phenomena. So again I will give you the example of that boiling water. So what happens from this heating source, heat will be radiated from this heating source to reach the bottom surface of my container. This bottom surface will gradually get heated up, and through convection that heat will be transferred to the bulk of the fluid, and then the bottom layers of the fluid will get warmed up, it will get lighter in weight, it will move up, and the colder water molecules will come down. In this way the whole water body will get heated up, so that it becomes that is your convection. And then whole water, when it gets heated up, then again the heat will be transferred to the wall of this container, and from this wall of the containers the energy will transferred to the adjacent molecules, and as a result even your handle, if it is of the same metallic structure or same material as this container, then it will also get heated up, means if it is not with any insulation. So this is the example of conduction. So everything happens in combination. So now again I'll go to the calculations of conduction. So if I want to calculate the conductive heat transfer, the one law which you will find everywhere is Fourier's law of heat conduction. So the basic equation is given as rate of transfer process equals to driving force by resistance. So anything, if anything, means if you want to do anything, you need a driving force that will accelerate your work, and then there will be something which will hold you back. So that is a resistance. So the rate of a transfer process means that is favored by the driving force, but it is inversely proportional to the resistance. So the above equation implies that to transfer a property such as heat or mass, we need a driving force to overcome a resistance. Just let me give you one of-bit example that you want to study. Okay, you want to study, you are studying. Now what is your driving force? Your driving force is to get good marks. Okay, so that will make you study harder. Now what will be your resistance? Your resistance can be your health condition, or you may want to watch some TV, or you want to have some slack time. So those are your resistance. Now your driving force means now your drive to perform better in exam should be high enough to overcome those slacking kind of thoughts, to accelerate your rate of study. So here also my driving force means here what will be the driving force for heat conduction? Temperature difference. So that temperature difference should be high enough to overcome the resistance of heat transfer. So now the transfer of heat by conduction through fluids or solids is given by Fourier's law. So Fourier's law, it is given by Qx by A equals to minus K into ddx of capital T. So Qx has a rate of heat transfer and means heat transfer rate in x directions. That is why this x of x is given. A is a cross-sectional area normal to the direction of heat flow. That is perpendicular to the direction of the heat flow. That should be your area. K is your thermal conductivity and capital T is your temperature, means absolute temperature in Kelvin or even in degree Celsius, and x is the thickness of the material. And the quantity Qx by A is called the heat flux, whose unit is watt per meter square. The quantity dt dx is a temperature gradient in the x direction, means that variation in temperature in that thickness, means so across the thickness. And the minus sign, this minus sign is required because if the heat flow is positive in a given direction, the temperature decreases in the direction. So why am I giving minus sign here? I am giving minus sign because when heat is flowing naturally, then gradually the temperature gradient will decrease, means it is flowing from higher temperature zone to the lower temperature zone. Now if it continuously happens, then gradually both the regions will be at the same temperature. So and temperature also decreases at the direction of the heat flow. So that is why minus sign is given here. Now consider a slab, means conductive heat transfer through a flat slab or wall. If you consider a flat slab, means just a wall, this room wall, if you consider like this. So Fourier's law can be integrated for the case of steady state heat transfer through a flat wall of constant cross-sectional area capital A, where the inside temperature is at T1. So suppose the inside temperature is at T1, there is a high temperature, and outside temperature at point 2 is T2, which is at lower temperature. And it is at a distance, means x2 minus x1, means here it will be x2, here it will be x1, and the thickness is delta x. So it is x2 minus x1 meter away. So how can I integrate it? So Qx by A, these are constant, it does not change with time. Only this thickness will change, means it will gradually travel from this port area to this area. So it will gradually change from x1 to x2. So integration from x1 to x2 dx equals to minus k, it will stay as it is, and temperature will change from T1 to T2. So integration from T1 to T2. So integrating, assuming that K is constant, means assuming thermal conductivity is constant, because thermal conductivity again depends upon the composition of the material. So we will consider it as constant, and it does not vary with temperature. And dropping the subscript x, means this is just for simplification. If I just drop the subscript x, so I will be left with Q by A equals to small k by x2 minus x1 into T1 minus T2. Means I have just integrated it. So it will becomes x2 minus x1. This is a definite integral. And here it will be T2 minus T1. But if I want to remove this minus sign, it will becomes T1 minus T2. So it becomes, means I will just bring this x2 minus x1 to the right hand side. So k by x2 minus x1 into T1 minus T2. Or this x2 minus x1 is nothing but my delta x. So it will be equals to k by delta x into T1 minus T2. This is for your one single wall. Now, if I consider thermal expansion of the material, so if the thermal conductivity is not constant but varies linearly with temperature, mainly applicable for liquids and gases, so here I was considering K as constant, but if I consider K not to be a constant, so here this is given by this empirical equation, that is K equals to A plus BT, where A and B are empirical constants. So in this case, I will consider this as an average, this T as average. So for varying K equals to A plus BT, then my equation will be changed into Q by A. So in place of K, I will write A plus B into T1 plus T2 by 2, means the average of T1 and T2 divided by delta X into T1 minus T2 as it is. So this is replaced by, means this is denoted by, this total thing is denoted by Km. So Km by delta X into T1 minus T2. So this means that the mean value of K is the value of K evaluated in the linear average of T1 and T2 in case K is not constant. Now as stated earlier, the rate of heat transfer process equals the driving force over resistance. Okay, so that is why this T1 minus T2, temperature gradient, is my driving force, and if I just bring this K to the denominator, so it becomes T1 minus T2 divided by delta X divided by Ka. So why Ka? Here this A, this Q by A was heat flux, so I'll just bring this A to the right hand side, so it will become here, so Ka by delta X. So if I just bring it down, so it will be delta X by Ka. So this delta X by Ka is my overall resistance, means for a single wall. So overall I can just say resistance. So driving force by resistance. This delta X by Ka is the resistance in Kelvin per watt. Now coming to two problems for this. So find the heat flux through a stainless steel slab having 10 centimeter thickness, which is maintained at 100 degrees Celsius on hot side and 30 degrees Celsius on cold side. The thermal conductivity of steel is 16.37 watt per meter degree Celsius. So it is saying that a steel slab is given. So a steel slab is given where here I have 100 degrees Celsius and here I have 30 degrees Celsius, and this thickness is my 10 centimeter. Okay, and thermal conductivity is given. So delta X is 10 centimeter. I'll convert it into meter, so it becomes 0.1 meter. T1 is, this is T1 and this is your T2. So T1 is given as 100 degrees Celsius, T2 is 30 degrees Celsius, K is already given. So just I will put it in the formula, Fourier's law, Q by A equals to K by delta X into T1 minus T2. So they have asked about heat flux, that's why I am writing Q by A. So K, value of K is given, value of delta X is given, T1 and T2 is given, so I will just get the heat flux. So just putting it into the formula. Then the next problem is the maximum tolerable heat loss through a furnace wall is 1.3 kilowatt per meter square. What is this? This is the heat flux. A brick wall is constructed next to the furnace wall to insulate the heat loss. Okay. So after furnace wall, from if this is the furnace wall, so there is a brick wall here. A brick wall is given. Okay, the temperature on either side of the wall is 200 degrees Celsius. Here it will be 200 degrees Celsius and here it will be 40 degrees Celsius. What should be the thickness of the brick wall? So I have to calculate the thickness of the brick wall. If the thermal conductivity is given as 0.72 watt per meter degree Celsius. So everything is given. Q by A, heat flux is given 1.3 kilowatt per meter square. I will convert it into watt if necessary. T1 200 degrees Celsius, T2 40 degrees Celsius and K is given. Again you put it in the formula. Just this one I don't know. Others are given. So delta X, so means after calculation putting all the values, I get 0.088 meter. I hope the problems are helpful for you. Now that was about the slab. Now let's come to the one single slab. Now if I consider a multiple slab or multiple wall, so in this case, in the case where there is a multi-layered wall of more than one material, so it will mean suppose this is one wall, this is another wall, this is means A, B, C. These are in series. So since the walls are in series, the heat flow Q must be same in each layer. So the value of Q will be same in each layer. If you have read about electricity, you will be able to understand it that Q won't change in this direction. So here for each of this material, I will have that individual Fourier's law. So for wall A, it will be K suffix A divided by delta XA into T1 minus T2 because the temperature gradient across wall A is T1 and T2. For wall B, it will be KBA divided by delta XB into T2 minus T3, because temperature gradient here is T2 minus T3, T2 and T3. And for wall C, it will be KCA divided by delta XC into T3 minus T4, because the temperature gradient here is T3 and T4. So solving each equation for delta T, if I just solve for all of this, so for T1 minus T2, it will be Q into delta XA by KAA. For T2 minus T3, it will be Q into delta XB by KBA. And for T2 minus T3 minus T4, it will be Q into delta XC by KCA. Now, if I add up all this, so T1 minus T2 plus T2 minus T3 plus T3 minus T4, so T2, T2, T3, T3 will get cut. I'll be left with T1 minus T4. So that will here, so I can take Q common here and I'll add up all those things. So delta X by delta XA by KA plus delta XB by KBA plus delta XC by KCA. So this is nothing but your overall resistance. Now if just rearranging it, so I'll get Q equals to T1 minus T4 divided by delta XA, means the whole thing will come here, and this is the resistance of wall A, this is resistance of wall B, and this is resistance of wall C, and this is resistance of wall A. So if you have seen the formula, so we can go to another problem for this composite wall. So for this composite wall, a cold storage, means one problem is given here. Cold storage room is constructed of an inner layer of 12.7 millimeter of pine, means 3 layers are there. Okay. A, B, C. So first layer is of 12.7 millimeter of pine, a middle layer of 101.6 millimeter of corkboard, this one B, and an outer layer of 76.2 millimeter of concrete. This one is concrete. Surface wall temperature is 255.4 Kelvin inside the cold room. So here it will be 255.4 Kelvin and 297.1 Kelvin at the outside of the concrete. So here it will be 297.1 Kelvin. So the thermal conductivities for pine, corkboard and concrete are given here. Now you have to calculate heat loss for 1 meter square. So area is given here as 1 meter square. Area is given as 1 meter square. And the temperature interface between wood and corkboard. Wood and corkboard, here it is, I have to find out the temperature at this interface. So here T1 is 255.4, so this is T1, this is my T4, and Ka means for this area, the thermal conductor KB, Kc, all are given, and delta XA, delta XB and delta XC are also given. A 1 meter square is given. So I can calculate resistance for each of the materials. For Ra, delta XA by Ka, I am getting. For Rb, delta XB by KBA, I will get 1, and for Rc also I will get 1. Then I will just add up all those in the denominator, and I know the value of T1, I know the value of T4, so I will put all the values. So I am getting result as minus 16.48 watt. This negative value indicates that the heat flows in from outside. So heat is flowing from this direction to this direction. So that is why, since heat is coming within the system, so it is negative. To calculate T2, so here it is, this interface is T2. To calculate T2 at the interface between pine and cork, so I need to find out, means in this area, I need to find out heat transfer in this area. So here it is nothing but Q equals to, Q will stay same, and I have got the value of Q. Q equals to T1 minus T2 by Ra. I know the value of Ra, I know the value of T1, I know the value of Q. So I can easily calculate the value of T2, which is coming as 256.79 Kelvin. You can check for yourself, you can calculate yourself to check the answers. Just by saying, it won't be that easy. So now for cylinder also, that was for slab. Now if I consider a cylinder, in most of our thermal equipments, those are in cylindrical form. Okay, so that's why I need to calculate what will be the heat transfer through a cylinder or for a sphere. So for a hollow cylinder, in many instances in the process industries, heat is being transferred through walls of thick-walled cylinders, such as a pipe that may or may not be insulated. You must have done problems of those, means heat flow through a pipe, insulation and everything. Now consider a hollow cylinder. So you consider this as a hollow cylinder. This is a hollow cylinder. Okay, with an inside radius of R1. So here the inside radius is R1. This is R1, I think. Okay, so the inside radius is R1, outside radius is R2. And where the temperature is T1, where the temperature is T1 means for inside radius the temperature is T1, and then outside radius of R2 having temperature of T2. So here it will be T2 here. And a length of L meter means the whole cylinder is of length L meter. Now heat is flowing radially from inside surface to the outside surface, means if hot water is flowing within the pipe, so from the inside to outside heat will flow. Temperature gradient T1 will be higher than T2. So it radially flows. So rewriting the Fourier's law, so instead of dx I will write dr here because I am concerned about radius here. So Q by A is the heat flux equals to minus K into dt by dr. Where cross-sectional area is normal to the heat flow for cylinder, it is 2 pi RL. R is the radius and capital L is the length of the cylinder. Now substituting equation 5.22 into equation 5.21. So I'll get Q by 2 pi L, and here since R is changing from R1 to R2. So I have to integrate from this dr will come here. Okay, so it will be means, and R I already have here, so dr by R integration R1 to R2. R1 to R2, and here minus K it will remain as it is, and temperature will change from T1 to T2. So here, so Q equals to K into 2 pi L, so means I am just rearranging it, and if I integrate R1 to R2 dr by R, so that is nothing but your ln R2 minus ln R1 is natural logarithm of R2 and R1, so it is nothing but R2 by R1, right? So I'll get this one. So that is why I'll get, if I rearrange it, Q equals to K into this 2 pi L will come here, K into 2 pi L divided by ln R2 by R1. So because that left hand, right hand side is coming to the left hand side, into T1 minus T2 as it is. Now multiplying the numerator and denominator by R2 minus R1, so what will I get? So this will stay as it is, so R2 minus R1 divided by ln R2 by R1 into T1 minus T2 divided by R2 minus R1. Okay, so that this one will give you this 2 pi L into R2 minus R1 divided by ln R2 by R1. This total will give you ALM, log mean area. Okay, so this will give you log mean area, so equals to T1 minus T2 divided by R2 minus R1 divided by KALM. So this total gives you the resistance or overall resistance. So ALM is log mean area. So log mean area is nothing but 2 pi R2L minus 2 pi R1L divided by ln into 2 pi R2L divided by 2 pi R1L. Means they are just putting 2 pi L within it. So if I simplify it, it becomes A2 minus A1 divided by ln A2 by A1. So this one means this R is nothing but R2 minus R is resistance, capital R is small r2 minus small r1 divided by KLM, or if I just break ALM here, so I'll get ln R2 by R1 divided by 2 pi KL. Now in engineering practice, if area 2 means if A2 by A1 is means the ratio of A2 and A1 is less than 1.5, the linear mean area of A1 plus A2 by 2 is within 1.5% of log mean area. Means if this ratio is below 1.5, so instead of log mean area, I can also use the average area. Now whenever we'll use the log mean area and whenever we'll use average area, some differences in the result will happen. Okay, some error may occur. So within this range it is tolerable, but if it is beyond that this percentage, then the error is quite substantial. So one problem is given here for hollow cylinder. A thick wall cylindrical tubing of hard rubber having an inside radius of 5 mm, that is R1 equals to 5 mm. I have also written it here, yeah. 5 mm and an outside radius of 20 mm is being used as a temporary cooling coil in a bath. So this is a cooling coil. So that means what? Cold water is passing through the pipe. Ice water is flowing rapidly inside and the inside wall temperature is 274.9 Kelvin. So it will flow from outside to inside. The outside surface temperature is 297.1 Kelvin. A total of 14.6 watt must be removed from the bath by the cooling coil. So within the hot water bath or anything or any water bath, so whatever heat is there, so a minimum or total of 14.65 watt must be removed. So how many meter of the tubing or how many meter of the cooling coil is required, means how long cooling coil you need to extract at least 14.65 watt heat. So the thermal conductivity is given here. So this will be given with the question. The thermal conductivity K at 0 degrees Celsius or 273 Kelvin is 0.151 watt per meter Kelvin. Since data at other temperatures are not available, this value will be used for the range of 274.9 to 297.1 Kelvin. So this is our given data. And what others are given? So R1 is given, that was 5 mm, converted into meter, you get 0.005 meter. R2 is given as 20 mm outside radius, so that is 0.02 meter. T1 within inside the pipe is 274.9 Kelvin and T2 297.1 Kelvin, and the Q is 14.65 watt given. This needs to be extracted. The calculation will be done first for a length of 1 meter. I don't know the length of the cooling coil, so that's why first I will consider 1 meter square area. Sorry, 1 meter length. For that I will calculate the area. So I'll have two areas there for R1 and R2. So for A1 equals to 2 pi R1L. So just put it into the formula of cylinder. So 2 into pi into R1 is given. Length 1 meter is given. So I'll get 0.0314 meter square, and A2 for R2 can also be calculated. So here it will be 0.1257 meter square. And log mean area, I know the formula, A2 minus A1 divided by ln A2 by A1. Just put all the values, you will get 0.0680 meter square. So I know the value of ALM, I know the value of K is given, yes, K is given here. T1 and T2 I know, R2, R1 I know. So put everything and I get for 1 meter tubing, the heat is minus 15.2 watt. Minus because heat is flowing from outside to inside. So for 1 meter, my heat removed is 15.2 watt. So 15.2 watt removed by 1 meter. So 1 watt heat will be removed by 1 by 15.2 meter, and 14.65 watt will be removed by 15.2 meter. So that is what given here, and I will get the answer of 1964 meter. Again, I am telling you, do it yourself to understand it better. So I told you that if I use average area instead of log mean area, there will be a difference in result. So one problem is given for that. So find the heat transfer rate per 1 meter length of a circular copper pipe of inside diameter 10 centimeter, outside diameter 12.5 centimeter. Inside temperature of the pipe is 100 degrees Celsius and outside temperature of the pipe is 40 degrees Celsius. Also calculate the percentage error involved by using average radius in place of log mean radius or average area in place of log mean area. The thermal conductivity of the metal is given here. So capital L is 1 meter given, R1 given, R2 given, T1 given, T2 given, K given. So I can calculate I can calculate A1, I can calculate A2. So from there I can calculate log mean area. So I can simply put it here. Yeah, through means if I am doing through log mean area. So this will be my formula. Now if I am using average radius, so I'll get average area. So for that, this is my formula. Means instead of log mean area, I'll just put the average area here. See, there is a difference in the result and the percentage error is given. So percentage error will be calculated based on means with respect to the log mean area. So for this I have just rounded it off. So 1442 minus 1432.08 into 100 divided by 1432.08 into 100. So the percentage error is coming as 0.69%. So that is quite substantial for practical purposes. Now let me just finish it with actually this is the second last topic. Means since I was talking about single slab, then I spoke about the multiple slab. So now I told you that in most of the food processing units we have to work with cylinders, we have to work with pipes. So that is why there also we may need multiple layering. So that is why just talking about a single pipe layer is not enough. So I need to work also with multi-layer cylinder. So in process industries, heat transfer often occurs through multi-layers of cylinders. As for example, heat is being transferred through the wall of an insulated pipe. Of course, I need insulation. Insulation is very important. So that is why multi-layer comes into the picture. Now this figure 5.6 shows a pipe with 2 layers of insulation around it. So 2 layers. This one is the primary pipe. After that, 1 layer of insulation, 2 layers of insulation. So total 3 concentric hollow cylinders are there, A, B, C. So temperature drop is T1 minus T2 for material A, T2 minus T3 across material B and T3 minus T4 across C. Heat transfer rate Q will be of course the same for each of the layer because it is in series. So I will have individually for T1 minus T2, T2 minus T3 and T3 minus T4. Okay, and then for this I have this log mean area for material A, log mean area for material B, log mean area for material C. Same formula as the single one but in series. So using the same method of combining the equations to eliminate T2 and T3 as was done for the flat walls. For flat walls also we did how to eliminate T2 and T3 just by adding all this T1 plus minus T2 plus T2 minus T3 plus T3 minus T4. So T2 and T3 will get cut. And then adding up all, so just like the composite wall, we will get it here T1 minus T4 divided by the individual components, means individual resistive components. So it becomes in simplified form Q equals to T1 minus T4 divided by RA plus RB plus RC, and or I can write T1 minus T4 divided by summation of R. Hence the overall resistance is again the sum of individual resistances in series. So here another problem is given, but I have not solved it here. This is for you. You do it. Just a little hint I will give here. A thick wall tube of stainless steel A having thermal conductivity K to 21.63 watt per meter Kelvin with the dimensions of 0.025 meter inner diameter and 0.0508 meter outer diameter, means OD, is covered with 0.0254 meter thick layer of an insulation B. Okay, so thick wall tube. So this is my tube of material A. Okay, so this will be my R1, this will be my R2, means or the total means this will be my OD, means ID, and this will be my OD, out inner diameter, outer diameter. I think I should give it like this. So this is my inner diameter and this will be my outer diameter. So this is given, and beyond that it is covered with 0.0254 meter of insulation. Okay, so this also has its individual thermal conductivity. The inside wall temperature of the pipe is given 811 Kelvin, outside temperature 310.8 Kelvin. Now for a 0.305 meter length of a pipe, L is given. Calculate the heat loss and also the temperature at the interface between the metal and insulation. So I need to find out the temperature of this portion. This I need to find out. Okay, and also the heat loss means I also have to find out Q. So for now, calling T1 given, T3 is given, T1 is given and T3 given. I need to find out T2. Now my R1 is nothing but your inner diameter divided by 2, R2 is your outer diameter divided by 2, and R3 is your insulation, means this means this plus 0.0254 plus 0.0254 meter will give you R3. Okay, so if you have all this, I think you will be able to do the rest of the problem because it is same as the slab problem. So there's the last part of your steady state heat transfer for this conductive steady state heat transfer. So we cannot rule out the sphere. I have spoken about slab, cylinder. Now we also work with sphere in process industries. So heat conduction through a hollow sphere is another case of one-dimensional conduction, that is heat flow in one direction only. Using Fourier's law for constant thermal conductivity with distance dr, where r is the radius of the sphere. So I am considering a sphere here. So I'll also have radius here, but only what is the change between cylinder and sphere? That is, the formula of area is different. In case of sphere, area is 4 pi r square, and in case of cylinder it was 2 pi rl. So cross section area is given. Again we will integrate it for the whole sphere. So this is 4 pi r square, so it will be dr by r square. Integration from r1 to r2 equals to minus k, and dt changes from t1 to t2. I'll just integrate it, and the final form will be q by 4 pi into 1 by r1 minus 1 by r2 equals to k into t1 minus t2, and the final form will be in this way, that is t1 minus t2 divided by r2 minus r1 divided by 4 pi r1 r2k. This is nothing but your resistance. Okay, so here I have not given any problem to show you, but anyways in the subsequent lectures I will also provide problems if needed, and you can ask me for any assistance. Thanks to all of you.